and for the opportunity to speak to you. I'm very sorry that I couldn't be there in person, but it sounds like it's a wonderful program, and I'm very grateful to be part of it. So I think originally the hope was that I would talk about the status of Higgs physics, but to be honest, I've been thinking quite a lot, mostly these days, about generalized symmetries, and I thought this was an opportunity to tell you about some of that. Of course, I know there will be more discussion of generalized symmetries and their applications to particle physics throughout the program. So I also wanted to spend a little bit of the time with my talk, maybe setting the stage for some of the discussion that would come. So what I'll tell you about today, the talk is sort of in three parts. One is just designed to give an introduction or an overview to relevant generalized symmetries for particle physics, if you haven't been thinking about this recently. And this is heavily inspired by Sungwoo's work, among many others. And then I want to tell you about sort of two examples where I think it's possible to learn some new things about particle physics by thinking in the language of generalized symmetries. So those latter two examples are based on work with Marius Kongsor and work in progress with Dan Sahayek. Okay, so I show this at the start of most of my talks these days. The idea being, I think, the situation we find ourselves in as particle theorists, more than 10 years after the discovery of the Higgs boson, is we spent a long time with sort of a lamppost that was guiding our thinking about physics beyond the standard model. And that lamppost, of course, was guided by questions about parameters of the standard model. And I think we've been surprised, in the last decade plus, that many of those ideas have failed to pan out experimentally at the LHC and elsewhere. But I think what we've realized, we've taken that as a great opportunity to recognize, in fact, that we were looking under a lamppost, and in reality, there's sort of a vast set of possibilities that now we're exploring more fully. And showing that vast set of possibilities as a sort of a sky full of stars is evocative, because I think we realize a lot of the opportunities for fundamental physics lie in cosmology and the interface of astroparticle physics. But there's also something more metaphorical about this, which is that I think this is true in the theoretical landscape, that there's a lot of possibilities just in the structure of quantum field theory that we maybe weren't aware of so much as particle physicists. And now we have this opportunity to understand these new methods and bring them to bear on the problems of the standard model. Okay, so that's the idea of looking beyond our familiar lampposts as particle theorists, not just experimentally, but also theoretically. And so here, of course, I have in mind. Yeah.
Okay.
It's paging okay? Good. Okay. So I want to tell you about, I want to focus today in terms of, looking outside the lamppost in the language of generalized symmetries. And again, I sort of want to give this to you in three parts. The first is just background for those of you, since generalized symmetries, of course, they've been, profoundly successful, I think, already in mathematical physics and condensed matter physics. They are being imported into high energy theory, into particle physics over the last few years. Again, due in no small part to Sungwoo's work. But for those of you who haven't been thinking about generalized symmetries, I want to spend a little bit of time just setting the stage so that you know what the important ingredients are before we try to apply them to some problems in particle physics. So to really get your mind oriented towards generalized symmetries, first I just want to give you a different way of thinking about something that's already very familiar. In other words, a new language for talking about familiar symmetries. And of course, with familiar symmetries, we're accustomed to doing something, in our introductory QFT textbooks, where if we have a conserved global symmetry, we construct a conserved current out of it, and we know we can construct a charge corresponding to that conserved current by taking, in this case, a spatial slice and taking the component of the conserved current normal to that surface, and integrating it over all of the spatial slice, and that gives us a conserved charge. And we know if we exponentiate that, then that creates a unitary, and that unitary has affects transformations on fields that are charged into the global symmetry. Okay, and so the first thing I just want you to do to imagine generalizing that picture is just to take a step from the idea of integrating this the time component of this conserved current on a spatial slice to instead imagine performing the same action on a general codimension one manifold of your space-time, so it doesn't necessarily need to be spatial. And so in very close analogy to what you're accustomed to. And we'll call this thing, because it's not necessarily on a spatial slice, we'll call it a symmetry defect operator. Okay. And it obeys these symmetry defect operators. They're not exactly unitaries, but they have many similar properties. And in particular, they recapitulate the set of symmetry defect operators that you can construct from a familiar global symmetry, recapitulates a lot of the nice properties of the symmetry group itself. So in particular, the symmetry defect operators that we can construct for the symmetry, they obey the group multiplication law in the sense if I construct a symmetry defect operator for one group element and for another group element, and I compose them, and they're on the same surface, then what that'll give me is a symmetry defect operator for whatever the group product was of those two elements. Okay. They're also what we'd say topological, which is to say that they're invariant under smooth deformations of these surfaces on which they're defined. And the way you make that precise is you could imagine taking a symmetry defect operator on some surface and taking the symmetry defect operator, whatever group element that original symmetry defect operator is defined for. You construct the symmetry defect operator for the inverse on a slightly different surface. And if these symmetry defect operators are topological, in other words, if it doesn't depend on the smooth deformations of the surfaces on which they're defined, then this inverse should really act like the normal group inverse, even though it's defined on a slightly different surface. And as long as the symmetry the current is conserved, this in fact is true. So that tells us that these objects are topological. And finally, they induce symmetry transformations on charged operators in exact analogy with how normal unitary operators, where we exponentiate a charge, induce transformations on charged operators. And so you can think in sort of a space-time picture, if you have a charged operator localized at a point, the action of pulling a symmetry defect operator across that charged operator has the effect of implementing a transformation on the charged operator in the appropriate representation. Okay. So the virtue of thinking about this, if you're familiar with global symmetries in this way, is it just gives you a new way of defining the symmetry. Okay, it recapitulates all of the properties of the symmetry group that you're accustomed to. But now it also gives you a leg up because it allows you to identify new types of symmetries that you can define in analogous ways, but are in some sense a generalization of what we're accustomed to. And so this was the central observation that was made in this famous paper now a decade ago by Gaeta, Kapustin, Seiberg, and Willett, which is to say, they propose just defining the symmetry of a quantum field theory by its symmetry defect operators and their relations, and recognizing that you could, define symmetry defect operators for all of the ordinary symmetries we're accustomed to, which act on charge operators localized at space-time points. You could generalize it to what they called higher form symmetries, where now the dimensionality of the charge objects increase. So in particular, for an ordinary symmetry, the dimension of the charge objects is 0-dimensional, and the conserved currents are 1-dimensional or one index conserved currents. Now you could imagine generalizing that to p-form symmetries, where the conserved currents are p+1 index currents, and they act on p-dimensional charged objects. And the beauty of symmetry defect operators is this allows you to define the notion of symmetries acting on these extended objects. Now, I should say at this point, although for the sake of particle physics, I try to stick with explicit index notation for comfort. At this point, differential forms are essentially obligatory just to handle the proliferation of indices. So I hope you'll forgive me for working in the language of forms. And just as a matter of convention, you'll notice throughout the rest of my talk, it's very typical if you have a conserved, p+1 index current to define the appropriate form as its dual, because that's the object that's closed as opposed to co-closed. Okay. And so then you can, for these generalized symmetries, you can construct symmetry defect operators where now as the dimensionality of the charge object goes up, the dimensionality of the symmetry defect operator goes down, and they go down in precisely a compensating way. So that there's always a well-defined linking between the charged operators in your theory and the symmetry defect operators. Okay. Now, one thing that you see immediately, you sort of ask yourself, okay, we're generalizing our notion of global symmetries to act on extended objects. What are the sets of properties that these are going to obey? And the first thing that you notice as a particle physicist is slightly disappointing, that these symmetries are necessarily abelian as soon as they are generalized beyond the familiar case of p is equal to 0. And a simple cartoon picture that tells you that this is true, I've just drawn here, where you could imagine, and now say in 3 dimensions, your charge operator is just a line. And now you can imagine encircling it with 2 different symmetry defect operators corresponding to 2 different group elements of your symmetry. And if you pulled both of these past the line operator, that would induce the symmetry transformations first by this element G1 and then by the element G2. But of course, these symmetry defect operators are topological, and so we can just deform them by small amounts, pushing down the G1 symmetry defect operator, pulling it out and bringing it back up, so that now it sits outside of the G2 symmetry defect operator. And now, having done that deformation, if I pulled them both past my charged operator, I would be implementing the symmetry transformations in the opposite order. And so these have to give me the same results. And so that tells us that this, in this case, one-form symmetry is abelian. So of course, as a particle physicist, we know a lot of symmetries, a lot of the most interesting things that symmetries do happens in the non-abelian case. So it's somewhat disappointing that here the physics is intrinsically abelian. But as we'll see, of course, there's still a lot of richness that persists. Okay, so these are not exotic symmetries, these higher form symmetries. They are ubiquitous in 4 dimensions, and they're really present in all of the symmetries, all the theories we're accustomed to thinking about as particle theorists. So just to give you a couple of concrete examples that we'll come back to over and over again throughout the rest of my talk. The first one, and the one I think that is the best for building intuition, is just to think about a pure U1 gauge theory, so Maxwell electrodynamics with no charged matter. And that actually has two these higher form symmetries, two one-form symmetries. One of them is what you would call the electric one-form symmetry. And the conserved current in this case is just the field strength tensor itself. So of course, in electromagnetism with no charged matter, the field strength tensor is a conserved current just from the equations of motion. Okay. Now, of course, the game is it's easy to identify some antisymmetric tensors constructed out of fields. The challenging thing to know if you have an interesting symmetry is to figure out if there are objects charged under the symmetry. And in the case of the electric one-form symmetry, there are. They're just the Wilson lines of the theory. So you could, again, think of Wilson lines as being world lines of electrically charged particles, but you could also just think of them as defining the spectrum of charged states in the theory. Okay. There's also a magnetic one-form symmetry. In this case, the conserved current is the dual field strength. And of course, in the absence of monopoles, this is conserved by the Bianchi identity. And the corresponding charge objects are the 't Hooft lines. Now, there's some other examples that are useful to think about in 4 dimensions. One of them is a periodic scalar or an axion, so something that has 2 pi f shift symmetry. And of course, we're accustomed to thinking, if we have an axion, to recognizing that that has a non-linearly realized zero form symmetry, the shift symmetry of the axion. But on top of that, it has a higher form symmetry, now not a 1-form symmetry, but a 2-form symmetry. And that means there's some 3-index conserved current. The 3-index conserved current is the sort of trivially conserved one, which is to say, if I take the Levi-Civita tensor and contract it with a space-time derivative and act on this periodic scalar, of course, if I hit that with another derivative, the anti-symmetrization of the indices will cause it to vanish. Okay, so it's sort of trivially conserved, but there are interesting charge objects, which are the world sheets of axion strings, okay, in a theory with a periodic scalar. The final example I want to give you is not of a continuous higher form symmetry, but of a discrete higher form symmetry. And in some sense, this is one of the original places where ideas about higher form symmetries really, I think, first came to be substantial. Is if you think about Yang-Mills theory with no charge matter, as we've known for a long time, Yang-Mills has a center symmetry, which is just formed out of the center of the group, and that's unbroken if there's no matter charged in appropriate representations. But in the modern language of higher form symmetries, we now recognize that the center symmetry is actually an alter example of a 1-form symmetry, and the charge objects in this case are the Wilson lines of the theory. Now, because the center symmetry of SUN is Zn, it's not a continuous symmetry, I can't write a conserved current, but it has all of the nice properties of a discrete symmetry now generalized to the higher form case. Okay, so I just want to emphasize these examples are ubiquitous in all of the theories that we care about. And so the real question is, do we learn, now that we recognize that these symmetries are in the theories that we care about, what do we learn by being aware of them? Now, I think the first thing that you should ask as a particle physicist interested in generalized symmetries, particle physics is not the art of exact symmetries. Particle physics is the art of broken symmetries, right? We spend most of our time figuring out the implications of selection rules that come from approximate symmetries in nature. And so it's useful to ask what happens, how these generalized symmetries are broken, and what happens in analogy to more familiar symmetries. So the first thing, of course, you'd like to ask is what does spontaneous breaking of higher form symmetries look like? And the answer is they can be spontaneously broken just like ordinary global symmetries. But that there's appropriate generalization, just as an ordinary zero form symmetry, if it's spontaneously broken, gives a Goldstone scalar boson. If you have a p form symmetry and it's spontaneously broken, it gives a p form Goldstone boson. Now you can work out a criteria for spontaneous breaking of these symmetries in analogy with ordinary zero-form symmetries. For an ordinary zero-form symmetry, we would say, okay, if I have some charge operator O, one way to define spontaneous symmetry breaking is to say, if I just look at the expectation value or the correlator of a product of two of these charge operators at different space-time points, as I take those points to be very separate, the expectation value should factorize into non-vanishing products of each of the operators. Okay. And a slogan might be, the spontaneous symmetry breaking if this expectation value depends on the points in which the operators are defined, but not on their separation. And that gives you some insight into what it would mean to define spontaneous symmetry breaking for the higher form symmetries. The appropriate generalization is precisely that. If there's an expectation value of a charged operator, which depends only on the surface on which the charged operator is defined and not on, say, the volume it encloses. Now, there's some subtleties having to do with absorbing infinite pieces in this definition, but basically speaking, for example, in a one-form symmetry where the charged objects are Wilson lines or Wilson loops, if their expectation values depend on the perimeter of the Wilson loop itself and not on the area, that corresponds to satisfying the criteria for spontaneous symmetry breaking in the one-form case. And so, of course, we're very accustomed to, when we learn quantum field theory in Peskin and Schroeder and Mark Zednicki's book, we, compute the expectation value of a Wilson line in electrodynamics. And indeed, we see that in the Coulomb phase, it has perimeter law scaling. And this is just a statement that this electric one-form symmetry of the Maxwell theory is spontaneously broken in the Coulomb phase. And so, because it's a spontaneously broken symmetry, one-form symmetry, there's a one-form Goldstone boson, and we would call that the Goldstone of spontaneous symmetry breaking. In this case, that would mean that the photon is the Goldstone boson of spontaneously broken one-form symmetry. Now, this is a sort of appealing picture because, up until this point, we would have said we would explain the masslessness of the photon either by invoking gauge invariance or by pointing out that massive and massless vector bosons have different degrees of freedom. But in some sense, this picture allows us now to put the masslessness of the photon on the same footing that we would put the masslessness of ordinary Goldstone scalars. Okay. So spontaneous breaking is great. The other question, of course, you have as a particle physicist trying to make use of generalized symmetries is explicit breaking. And here, the slogan I just want you to keep in mind is that charged matter explicitly breaks higher form symmetries. But what I mean by charged matter here is not the objects charged under the higher form symmetry itself. I mean, again, as we've seen in these examples, the higher form symmetries typically arise because the theory has a gauge symmetry. For example, in Maxwell electromagnetism, there was just the UN gauge symmetry itself, or in the theory of a periodic scalar, that itself is in some sense a gauge symmetry. And so it's the things that are charged into the gauge symmetry that's related to the higher form symmetry. If those degrees of freedom are present, they explicitly break the higher form symmetry. So again, just coming back to the one-form example of the electric one-form symmetry of UN electrodynamics, if I have charged matter under the UN gauge theory, that explicitly breaks the one-form symmetry. And there's sort of two ways of saying this. One is that if I have charged matter, then of course that means we said previously the electric one-form symmetry was conserved by the equation of motion. But now if I have charged matter, the equation of motion has a matter current on the right-hand side. And so of course, the current is no longer conserved, and the corresponding symmetry defect operators are no longer topological. Another way of saying it is if I have dynamical charged matter, of course, I can end Wilson lines on dynamically charged matter. And once I can do that, once Wilson lines become endable, the symmetry defect operators that would enact symmetry transformations of the one-form symmetry, those no longer have to link the Wilson line. I could always bring them around the end of a Wilson line that ends on a charged object. And so I can pull them past charged operators without inducing symmetry transformation. So the symmetry no longer acts in a well-defined way. Okay. There is something a little peculiar. So it's very easy to break these symmetries. But on the flip side, how broken they are and the effects of the breaking is actually quite different from what we're accustomed to for ordinary zero-form symmetries. If you have an ordinary zero-form symmetry, and let's say you break it in the ultraviolet even by a very small amount, by some irrelevant operators, we know that typically has a very dramatic impact on the infrared. For example, explicit breaking of global symmetry in the UV gaps the Goldstone bosons in the infrared. Something very different happens if we have explicitly broken higher form symmetries, because although they can be broken in the presence of dynamical charged matter, if that dynamical charged matter has a scale, the symmetries appear to become essentially exact. They're emergent and very good emergent symmetries below the scale of the mass of the charged matter. And so this is very different from what happens with zero form symmetries. Just to give you again a very concrete example, if we thought about electromagnetism and now we imagined adding a charged fermion to it with some mass, of course, with that charged matter is present, that energy is above its mass, the one form symmetry is explicitly broken. But as soon as we go below the mass of the charged particles, we can integrate them out and we can enter into an effective theory that's just the theory of the gauge bosons with some irrelevant operators. And of course, those irrelevant operators, they are given by the Euler-Heisenberg Lagrangian. And so, although naively it seems like the conservation of the one-form symmetry current, given by the field strength, is violated by these irrelevant operators, all of the irrelevant operators that show up are of the particular form that you can actually just define an improved current that's conserved in the infrared. Okay. So in some sense, this higher form symmetry, although it's broken above the mass scale of charged matter, it becomes nearly exact at low energies below the mass of the charged matter. And this is very different from what we're accustomed to for ordinary zero form symmetries. Now, I should say, talking about how good the symmetry is, this higher form symmetry is with reference to some Lagrangian or effective action can be slightly misleading because, as we've said, the objects that are charged in the higher form symmetries are extended operators. And so we shouldn't expect to see the effects of explicitly breaking these symmetries in some Lagrangian written in terms of local fields. Indeed, in this case, where the one form symmetry is emergent below the mass scale of the charged objects, although the symmetry appears to be exact once you go below the mass scale of the charged particles, if you wrote down an effective theory of the Wilson lines in the infrared, you would see the imprints of explicit breaking more explicitly. They would, however, be exponentially suppressed. Okay. Okay, I want to say one more thing about breaking of higher form symmetries before we start to get to some examples and applications to particle physics. So if you can bear with me for just a couple more minutes for setting the stage. We sort of know there's kind of three interesting ways to break a symmetry, right? We can spontaneously break it, we can explicitly break it, but we can also break it with an anomaly. And there's really two senses in which, in the presence of anomalies, higher form symmetries also take on a lot of interesting character. We can have breaking of symmetries due to 't Hooft anomalies. So remember, 't Hooft anomalies are not genuine anomalies of a theory. They're anomalies that emerge when we imagine coupling background gauge fields to global symmetries. And then we can also have genuine anomalies where there's actually some dynamical gauge fields that induce a conventional anomaly of the global symmetry. And in both of these cases, higher form symmetries actually give rise to very rich and interesting structures. So if we just have 't Hooft anomalies in the presence of higher form symmetries, what we end up with is something called a higher group structure. Whereas if we have genuine ABJ anomalies in the presence of higher form symmetries, we end up with what are called non-invertible symmetries. And I don't want to get deep into details about either of these, but I just want to say a few things that are going to be important for thinking about phenomenological implications in particle physics. So let's start with the higher group case, where we imagine that we've got some higher form symmetry and we have some 't Hooft anomalies in the theory, which should somehow be telling us about the structure of the theory as a function of scale. So just to give you a very concrete example, this is from the original paper that sort of articulated the structure of higher group symmetries by Cordova, Dumitrescu, and Trilogator. Just think about a situation in 4 dimensions where you have a real U1 gauge theory and 4 fermions, each of which transforms both under the gauge symmetry and under a zero form ordinary flavor symmetry of the theory. Okay. So I picked the charges, put them on the table here, and the charges are such that there's no ABJ anomalies. The flavor symmetry is not ABJ anomalous, but there is what you might call a 't Hooft anomaly. And I'm going to put scare quotes around 't Hooft anomaly because it's not a true 't Hooft anomaly where each of the 3 group factors is a global symmetry. It's a 't Hooft anomaly where one is the gauge symmetry and the other 2 are global symmetry currents. So this is, in some sense, a generalized 't Hooft anomaly, and it's non-vanishing with the charge assignments we've made. Now, the theory also has a higher form symmetry. So the electric one form symmetry is broken because we have charged matter, but there's still that magnetic one form symmetry because we don't have any monopoles. And so now we can sort of study what's the implication of having these 't Hooft anomalies in the presence of a higher form symmetry. Now, whenever we analyze the consequences of 't Hooft anomalies, what we do is we imagine turning on background gauge fields and coupling them to the global symmetry currents and seeing if that activates an anomaly. And in this case, if we turn on background gauge fields and couple them to our global symmetry, of course, the magnetic one form symmetry is a good symmetry of the theory. But because of the 't Hooft anomaly, this zero form global symmetry is anomalous. Okay. So the current in this case is no longer conserved proportional to the 't Hooft anomaly coefficient. And so if we just asked if we did a background gauge transformation, what would happen to the action? Well, we would get some change in the action due to the anomaly. And that change in the action is proportional to the field strength of the actual UN gauge field and the field strength of these background gauge fields that I coupled to the global symmetry current. But since we've turned on background gauge fields, not just that couple to the zero form symmetry, but also that couple to the one form symmetry, there's a term in our action where if we choose a specific gauge transformation of the background gauge fields coupled to the one form symmetry, we can use it to cancel off the anomalous variation of the zero form symmetry. Okay, so in some sense, the existence of a one form symmetry makes it possible to cancel off the anomalous variation of the bad zero form symmetry and render the theory consistent. Now, at this point, you're probably asking yourself, why do I care, right? We're playing this imaginary game of coupling background gauge fields to our global symmetries and asking under what situations is the theory rendered consistent. But it turns out this has a very interesting implication. In the same way that originally 't Hooft thinking about 't Hooft anomalies also told us a lot about the infrared dynamics of strongly interacting theories. And in this case, the idea is the following. Now, typically, all these symmetries, ordinary global symmetries and higher form symmetries, they're emergent in the infrared because they're usually broken by things in the ultraviolet. Now, we've seen the one form symmetry is good on its own. The zero form symmetry is not, right? It would have this 't Hooft anomaly. And so we expect, but it's the existence of the one form symmetry that renders the theory consistent. So you expect very generally that if both of these symmetries emerge as a function of scale, the one form symmetry should always emerge at or above the scale where the zero form symmetry emerges. If it were the other way around, you would enter some regime where the theory was inconsistent, where you had a sort of 't Hooft anomalous global symmetry with nothing around to fix it up. Okay. And that's a very powerful statement because that's like a general non-perturbative statement about any UV completions of this theory. And as a particle physicist, this should be exciting because we deal primarily with EFTs and emergent symmetries. And if we have this higher group structure, we immediately have a set of rules about the behavior of its possible UV completions. So this kind of thing should get us very excited. Now, in the example that I've given you here, it turns out this emergence inequality is sort of trivially satisfied. You could think about a UV completion. In the interest of time, I'm just going to say this very quickly. But for example, if you imagine that the U1 gauge group came from actually an SU2 that was spontaneously broken, at that scale, the one form symmetry would emerge and the zero form flavor symmetry would emerge. So that would be an example of the one form symmetry and the zero form symmetry emerging at the same scale. But it turns out in any UV completion you try to write down, this emergence inequality is always satisfied. So it's sort of a very powerful indication. And that's the sort of thing that we might try to put to use in particle physics that we care about. I just want to say something briefly about the second case of an anomaly, where instead of a 't Hooft anomaly, we have a genuine ABJ anomaly. And this puts us in what we've called a non-invertible symmetry. Yeah, I think you'll hear a lot more about non-invertible symmetries in Sungwoo's talk. So I'm just going to say something very concise here. Basically, what happens if you have a global symmetry that has an ABJ anomaly is you might have tried to construct symmetry defect operators for it, following the rules that we've laid down. But because of the anomaly, the symmetry is no longer conserved, and that's an obstruction to constructing the symmetry defect operators. It turns out you can go ahead and construct modified symmetry defect operators, but the properties of those modified symmetry defect operators, they don't recapitulate a group structure, but instead they typically recapitulate a fusion algebra. And one consequence of that is that not every element in this algebra has an inverse. Okay, so that's why we call it a non-invertible symmetry. To give you a very concrete example, if we just took a 40 UN gauge theory that had an axial symmetry that we know is going to be anomalous, the axial anomaly means that the symmetry defect operator for the axial symmetry is no longer topological. If you take the symmetry defect operator and its inverse defined on slightly different surfaces, they no longer act like one no longer acts like the inverse of the other. But what you can do is define an improved current that's conserved but not gauge invariant, and then improve it further by basically referring to a topological field theory that lives on the symmetry defect operator itself. And that allows you to define a well-defined notion of a symmetry defect operator in these cases. We don't care about all those details for my talk. All we really care about is once you do that, what you learn is, in fact, that if you bring together a symmetry defect operator and its inverse, instead of getting the identity, you typically get it proportional to a symmetry defect operator of a higher form symmetry of the theory. in this case of a UN gauge theory with an axion anomaly, if you bring together one of these operators in the inverse, it's proportional to the symmetry defect operator of the magnetic one-form symmetry of the UN gauge theory. And the reason I mention this is that there's a lot more detail here that we need, but there's in these cases similar statements about emergence apply. So in this case, the anomalous zero-form symmetry with the ABJ anomaly is the bad symmetry, and the good symmetry is this magnetic one-form symmetry. And so similar statements about the magnetic one-form symmetry emerging above the scale of the axial symmetry apply in the case of non-invertible symmetry, much like they did in the higher group case. Okay. So this was thanks for letting me spend the first half of my talk just giving you an overview of some of the important ideas and objects that might involve generalized symmetries as applied to particle physics. Of course, there's been a beautiful literature over the last 3 years of identifying generalized symmetries in contexts relevant to particle physics and really trying to use them to break new ground. So I don't have time here to go into all of these examples, but I just want to give credit where credit's due to a lot of the beautiful work that has happened, a lot of it driven by Shuheng Xiao and Clay Cordova, Sungwoo Hong, and collaborators. And at this point, we've seen how non-invertible symmetries can be related to neutrino masses. Non-invertible symmetries also play a role in axions. The standard model has higher group symmetries involving its fermions, and that has an interesting interplay with unification. There are implications of these symmetries and dynamics of cosmic strings, which I think Sungwoo will probably say something more about later on today. Peche-Quinn symmetries and other symmetries that we care about for problems of the standard model can be thought of productively as being non-invertible. And there can be other implications, for example, new particles, the global structure of the standard model gauge group, Yukawa textures, and so forth. So I don't have time to do any of these justice today. I do want to point you, if you're interested in learning about generalized symmetries, there's a beautiful introduction to generalized symmetries for particle physics by Sungwoo and Daniel Brennan that really is meant to bring you up to speed on the necessary methods. But what I want to do with the rest of my talk today is turn now to give you 2 examples where I think we also stand to learn more things about familiar particle physics by thinking about them in the language of generalized symmetries. So those 2 things that I want to tell you about, the first one is I want to tell you about the relation of generalized symmetries to the axion quality problem and extra-dimensional axions. And then in the last part of my talk, I want to tell you a little bit about non-invertible symmetries in the standard model in their relation to unified theories and monopole catalysis violation of standard model global symmetries. Okay. Maybe I'll pause here in case there's any questions just about the broad introduction. Should I go ahead?
Let's continue.
Okay, all right. Okay, so now let's go into generalized symmetries and the axion quality problem. So the axion quality problem, I know there's a lot of axion talks in the program at this workshop, and so probably it doesn't need too much introduction, but let me just say a few things about it. So of course, the axion we think of as a compelling candidate for solution to the strong CP problem. And the way that we're used to thinking about axions in extensions of the standard model is to recognize that it can be the pseudo-Goldstone boson of a spontaneously broken Peche-Quinn symmetry. So we imagine there's a Peche-Quinn scalar out there that gets a VEV, breaks the symmetry, and the axion is the corresponding phase. And by assumption, the way that the axion operates to solve the strong CP problem in the standard model is we assume that this symmetry is an exact symmetry only broken by the QCD anomaly, which gives the axion its periodic potential. And so under those conditions, of course, the VEV for the axion neutralizes the theta term of QCD at the minimum of its potential, and we've solved the strong CP problem. But again, the assumption was that the global symmetry of which the axion is a Goldstone was exact up to only one effect that broke it, which was explicit breaking from QCD via an anomaly of the Peche-Quinn symmetry. Of course, as an effective field theorist, you know that you should be also open to the possibility that global symmetries are broken by additional effects in the ultraviolet. And in this case, the global symmetry that solves the strong CP problem has to be such a good symmetry because theta is bounded to be so small that it's exquisitely sensitive to UV corrections that would violate the symmetry. So if you just imagined writing down irrelevant operators suppressed by some scale that violate the Peccei-Quinn symmetry, you find that indeed the presence of these additional operators gives rise to contributions to the axion potential whose minima are not at the minima given by the QCD contribution. And it turns out that, of course, if you might hope that as long as the scale of these irrelevant operators is sufficiently large, that these corrections to the potential would be benign. But even if the scale comes from M-Planck, ordinary four-dimensional M-Planck suppressed physics, for the axion decay constant in the regime that we find compelling, it turns out that these irrelevant operators are enough to spoil the solution to the strong CP problem, unless we forbid the operators to surprisingly high degree. Okay. And it turns out this isn't just the naive expectation from effective field theory. If you really do think about toy models of coupling this global symmetry to gravity, there are wormhole contributions that give rise to global symmetry breaking at the expected size. Now, there are many model building solutions. We've known about this problem since the early 90s. And so there's a plethora of ideas for how to solve them. And I apologize for not having the space here to give them all fair credit. But I think it's reasonable to say that all of these attempts to solve the problem complicate the simplicity of the axion as a solution to strong CP. But there is, I think one vastly preferred possibility for rescuing axions as a solution to the strong CP problem that doesn't require extensive engineering of the Peccei-Quinn sector, which is just to think about axions arising not from spontaneous breaking of symmetries in four dimensions, but instead axions arising from higher dimensional theories. Now, of course, this has a very long history in string theory, but all of the essential physics can be understood in field theory in 5 dimensions. And so I just want to stick, for the purposes of my talk, I just want to stick to the field theory examples. So the simplest toy model, of course, how this works, and I know many of you in the audience are very familiar with this idea, so I'll say it rather quickly. If you just imagined a 5-dimensional theory with a U1 gauge theory living in the bulk, and you compactified one dimension on a circle, of course, your 5-dimensional theory, you start off with the action for that 5D U1. We want to have a version of QCD in the theory, so let's just imagine for our purposes that's some SUN theory. That's our toy for QCD. And we're going to need a coupling at the end of the day between our axion and QCD. And so that means in the 5-dimensional theory, there's going to be Chern-Simons-like coupling between the U1 gauge field and the field strengths of the SUN. Then when we dimensionally reduce the theory, we compactify one dimension on a circle. We can decompose our 5D U1 into a 4-dimensional U1 and an extra pseudoscalar mode. And we can think productively then about what happens when we integrate that additional mode around the circle that we're compactifying. Okay. And what we obtain, the dimensional reduction, if we look at the lowest lying states, the zero modes, what we see is we obtain an axion-like degree of freedom, which came from the 5th component of the U1 gauge boson, a sort of a 4-dimensional SUN theory. And now we have an axion GG dual coupling that we expect from an axion like in QCD. And the axion decay constant in this case is set by the 5-dimensional gauge coupling and the radius of compactification. Now, why is this an interesting way of solving the extra-dimensional equality problem? Well, it was put very concisely by Arkani Hamed and Lisa Randall and collaborators in their paper on extra-natural inflation more than 20 years ago, where they were interested in using this idea not necessarily for the strong CP problem, but just for thinking about inflationary models with very flat potentials. And the way they characterized it, why this was a good idea, was that this extra component of the A5 of the gauge field propagating in the bulk cannot have a local potential due to the higher dimensional gauge invariance, and a shift symmetry protects it. Similarly, what happens to 4-dimensional Namber-Goldstone bosons. And they go on to say that the effects that break the symmetry are exponentially small. But you sort of know it's a very compelling explanation. It's a very interesting idea, but you sort of know that this can't be the whole story. One of them is that, as we're taught from our earliest age as particle physicists, gauge symmetry is a redundancy of description rather than a genuine symmetry. And so you would like to understand what is the actual symmetry at play. We also understand that simply invoking extra-dimensional gauge invariance actually isn't enough to understand why extra-dimensional axions are so effective. For example, extra-dimensional gauge invariance is also consistent with adding a bulk mass term for the UN gauge field, and adding such a mass term would give a mass to my axion, which is not exponentially small. So it can't simply be the case that extra-dimensional gauge invariance explains the lightness of an axion that comes from this setup. And finally, the reason you'd like to have a better symmetry understanding of what's going on in this configuration is that you would like to understand all of the possible ways that you can break the symmetry and give the axion a mass. And so you would really like to characterize the symmetry itself so that you can understand what effects might contribute to the axion potential at the end of the day. Okay. So the moral of this part of the talk and the purpose for thinking about generalized symmetries is just that rather than thinking about this axion as protected by a five-dimensional gauge symmetry, you should recognize that in this theory, what's actually happening is the axion is being protected by the five-dimensional one-form symmetry of the 5D gauge theory. Okay, and when you sort of say it, it's kind of a blindingly obvious statement, but surprisingly, this observation that we could think productively about the higher form symmetries of the five-dimensional theory as protecting the effective four-dimensional axion. This, as far as I know, wasn't made until Matt Rees's TASI lecture notes in 2023, and has been expanded upon both in a paper by Matt Rees and by my own work. Okay, so how is this working? So how should we think about the higher form symmetries of the five-dimensional theory as explaining why this four-dimensional axion is so well protected against the quality problem? Well, remember, we said in four dimensions, if we just had a UN gauge theory, it had an electric one-form symmetry and a magnetic one-form symmetry. In five dimensions, the high-form symmetries, we still have an electric one-form symmetry. Now the magnetic symmetry is a two-form symmetry because the dual now is a three-index object, and so that corresponds to a two-form global symmetry. And so the basic story of what's happening for an extra dimensional axion is that the real number shift symmetry of the axion is actually just embedded in the electric one-form symmetry of the 5D gauge field. And we've already talked in the first part of my talk, I spent a lot of time talking about how interesting the effects of explicit symmetry breaking are, and that there's a sense in which explicitly broken one-form symmetries look almost exact below the mass of charged particles, up to exponentially small effects that can be visible in the effective description of the Wilson lines. And it's that difficulty, or it's that difficulty of breaking higher form symmetries and the infrared robustness of emergent higher form symmetries that explains why the axion in this case is protected against the quality problem. Okay. So just to give you a picture to orient yourself, again, in five dimensions, we have the one-form symmetry, electric one-form symmetry, and magnetic two-form symmetry. Under dimensional reduction, when we compactify the fifth dimension on a circle of radius r, the electric one-form symmetry decomposes into a four-dimensional one-form symmetry of that four-dimensional gauge field, and the scalar zero-form symmetry that we recognize as the axion shift symmetry. The magnetic two-form symmetry is also very interesting to track because under dimensional reduction, it of course gives us a magnetic one-form symmetry of the four-dimensional gauge field, but it also is what gives us the two-form symmetry of the axion itself, right? As I noted much earlier, periodic scalars in four-dimension two-form symmetry. And in this situation, we can see the extra-dimensional axion, its two-form symmetry actually starts its life as the magnetic two-form symmetry in five dimensions. And the virtue of just making this concrete is that it now allows you to explicitly enumerate all of the ways that you can break these higher form symmetries that protect the axion, and therefore allows you to calculate once and for all in a very simple way all of the possible contributions to the axion potential. So as we've said, if we just had a free Maxwell theory in five dimensions, the electric one-form symmetry would be conserved from the equations of motion. The magnetic two-form symmetry would be conserved via the Bianchi identity. And now we can just go through all of the possible ways. I already laid out all the ways to break these higher form symmetries. We can just go through that list now for the electric one form symmetry and see what would give the axion a mass. Okay. And the answer is, as we've noted, we can break the electric one form symmetry directly with matter that's charged under the U1 gauge theory in five dimensions. We can break it with anomalies. It actually turns out there's something else very interesting we can do. We can break it by gauging the magnetic two-form symmetry. That turns out to break the electric symmetry. And then finally, there's something we can do which doesn't break the electric one-form symmetry. It actually makes it exact, but gets rid of the axion. So we can also gauge the electric one-form symmetry. Okay. So here I've just enumerated all of these possible effects. And I think actually in the interest of time, I'm going to pass quickly through the slides in which I go through them in detail. But let me just tell you about this table. And I'll leave the rest of the slides as details, and I'm happy to answer questions about them later. So what this table is showing you is each of the ways that you could modify this electric one-form symmetry that's protecting the axion. It's telling you how the current conservation is violated by those effects. It's telling you what the remnant symmetry is that's left over. and it's telling you the sort of potential that the axion acquires. So if we just look at the first line, we can say, okay, we know we could break the electric one-form symmetry by adding matter charged under the bulk UN gauge theory. And obviously that violates the current conservation because now there's a matter current that appears on the right-hand side by the equations of motion. Now this preserves a residual discrete one-form symmetry depending on the charges of the matter. And the existence of this matter gives the axion a potential. Basically, heuristically, we can think of if we are winding the electrically charged matter around the extra dimension, that winding number labels a theory with different selection sectors. And depending on the number of windings, that will induce a potential for the axion in 4 dimensions. And so indeed, we find from explicit calculation that the axion acquires a potential, which is exponentially small in the size of the extra dimension relative to the mass of the 5D charged particles. All right. The next thing you can do is actually gauging the magnetic two-form symmetry. So that means you turn on some 3-form gauge fields in 5 dimensions that couple to the magnetic two-form symmetry. That also violates the current conservation of the electric one-form symmetry, and it breaks down the electric one-form symmetry to discrete subgroup. Now, this just turns out to give, if you do this, this gives a direct tree-level mass to the axion. It turns out this is in some sense dual to turning on a Stuckelberg mass for the 5D gauge theory. And so this is just another way, if I gauge the magnetic one-form symmetry, I explicitly break it and I give the axion a mass. So that's how we can understand the axion getting a mass from the Stuckelberg mechanism. We can also gauge the electric one-form symmetry. That's the third line here in this table. Now, that actually doesn't break the symmetry. It makes it exact, right? We've now gauged it. But the problem is, by gauging it, we now eat the axion. And so the axion actually becomes a mode of a gauge boson of gauging this one-form symmetry. And so it disappears from the effective theory. Okay, so we're no longer solving the strong CP problem because we've eaten the axion. And then finally, the electric one-form symmetry can have an anomaly. The simplest anomaly it can have, of course, is an anomaly with QCD. And this is, in fact, just the way that we give the axion a potential from QCD. But the thing I want to emphasize is any other anomalies, either with other non-abelian groups or with abelian groups that have monopoles present, all of those will also give contributions to the axion potential through the anomalies. So the anomaly structure of this electric one-form symmetry also tells us about additional sources of breaking. And so having made this enumeration, now we're in a much better position to understand why the axion that comes from next dimension has such good quality. It's very hard to explicitly break the one-form symmetry. If we do, the effects are exponentially small. There are, of course, other effects that are not exponentially small, but each of these is in some sense discrete. Either it's present or not present. And we can imagine, indeed, that it's a consistent theory to have these effects be absent. Okay. In the interest of time, I've got slides that go through each of these effects in more detail, but I'm just going to leave them for everyone to look at, and I'm happy to discuss them later if you're interested. The thing that I just want you to take away from this is this gives us a very nice way of understanding why axions coming from extra dimensions are so protected against the quality problem, what the effects are that can give them a mass, and then finally how they might relate to the effects of quantum gravity. Because, of course, in telling you this story, I haven't said anything about gravity. I just gave you a toy model of a gauge theory in an extra dimension. But we have, of course, at this point, a very powerful swampland program with a whole suite of weak gravity conjectures in diverse dimensions that tell us about minimum masses of charged particles given gauge symmetries in the theory. And because we've seen that the presence of charged particles translates into potentials for axions, we can use the weak gravity conjectures in 5 dimensions to understand approximately where charged particles have to appear relative to the Planck scale and the size of contributions they should give to the axion potential. And again, in the interest of time, I'll just say this briefly. It turns out you can go through all of the appropriate weak gravity conjectures. And what you learn is, indeed, although it tells you there must be electrically charged matter present, which will break the one-form symmetry and give the axion a potential, all of these effects are sufficiently exponentially small that the axion quality is preserved. So from this exercise, by understanding the extra dimensional axion as being protected by a one-form symmetry in 5 dimensions, we can also better understand why indeed it's protected against the axion quality problem. Okay. Now, this is an example, so hopefully you found this interesting. This is an example, I would say, of it would be too much to say that we've learned something dramatically new from applying generalized symmetries to thinking about extra-dimensional axions. Instead, what it gave us is a very satisfying and complete picture of why it is that extra-dimensional axions are so well protected against the equality problem. And it allowed us to satisfyingly enumerate all of the possible effects that could be important for its potential. For the last bit of my talk, just the last 10 minutes, I want to take you through one more example where actually I think we learned some things that maybe we hadn't even entirely been aware of before that are relevant for phenomenology. And this now comes back to this idea of emergent symmetries and how the scales of emergent symmetries are related by higher group and non-invertible structures. So to motivate this, I want to briefly summarize actually a lovely paper by Clay Cordova and Seth Corrin from 2022, which had to do with the generalized symmetries that are present in the standard model itself. So of course, as we all know, if you take the standard model fermions and you turn off all of the Yukawa couplings, the maximal global symmetry of the standard model fermions is a U3 to the fifth symmetry, right? U3 for every fermion type, and we have 5 such fermion types, and so it's U3 to the fifth. Now, there's something very interesting. So that's the ordinary global symmetries. Of course, the standard model also has some higher form symmetries, and in particular, hypercharge in the absence of monopoles has a magnetic one-form symmetry. And it turns out that the flavor symmetry of the standard model forms a higher group structure with this magnetic one-form symmetry because individual factors of the standard model flavor symmetry participate in a higher group. They have these 't Hooft anomalies that I described earlier. Here I've listed this table, just the U1 factors of the U3s, but there's also up to a rescaling similar anomaly coefficients for the SU3 parts. Okay. And so what you'll notice is if you take a single U3 factor of the standard model flavor symmetry or an SU3 factor, it has a 't Hooft anomaly, okay, and therefore participates in higher group structure. But there are also combinations that I can make of several of those symmetries in which the total 't Hooft anomaly coefficient vanishes. Okay. Now, if you cast your mind back to the earlier part of my talk, I said if you have one of these higher group structures, it's very interesting because it tells you if the one form symmetry is emergent as a function of scale and the zero form symmetry is emergent as a function of scale, the one form symmetry has to emerge before or at the scale of the zero form symmetry. And this is, in this case, it tells you the magnetic one-form symmetry of hypercharge, that's the good symmetry. It should emerge at or above the scale of the standard model flavor symmetries. Okay. And there's a beautiful observation then that was made by Clay and Seth, which is that if you think about unifying the standard model into a unified gauge group, of course, in unified theories, there are monopoles corresponding breaking of the gut group down to the standard model. And so those monopoles are the scale, below the scale of the monopoles, that's when the magnetic one-form symmetry of hypercharge emerges, okay? But you take that statement and the two-group structure of standard model flavor symmetries, and that tells you that any individual standard model U3 symmetry, flavor symmetry, cannot be a good symmetry of the unified theory on its own. It has to emerge below the scale of unified symmetry breaking. However, there are combinations of the standard model symmetry groups that are anomaly-free. Those can be good symmetries of the unified theory. And this, in fact, is in one-to-one correspondence with the possible unification of standard model fermions into unified multiplets. Okay. So it's a very beautiful way of using this emergence conjecture in higher group structures to map out the space of possible unified multiplets of the standard model. Now, this is something, of course, we already knew how to do. The enumeration of unified erupts of standard model fermions was done in the 80s, but it's a very nice way of seeing it all come out at once from the generalized symmetries of the theory. But having told you that, what I want to draw your attention to is a related piece of the story, which wasn't present in Seth and Clay's paper on this, but is something else that is also present in the theory, which is you can ask, how is the emergence inequality satisfied? In other words, if I have my theory, my standard model, it's embedded in a unified theory, the one-form symmetry emerges below the scale of gut monopoles, and the emergence conjecture says the zero-form symmetries cannot be good symmetries above the scale of the monopoles. So what's going on to enforce this in our theories? And the answer is an effect that we've known about since the 1980s, which is monopole catalysis, violation of global symmetries. So of course, this is an old story originating with Kalin Rubikoff. The idea that most of us are accustomed to, for example, comes from SU5, where the idea is that in SU5 we have gut monopoles, and at the core of the monopoles we of course have X and Y gauge bosons that catalyze baryon number violation. And so we think about if you scattered a proton off of a monopole, that would catalyze the decay of the proton itself. Okay, and the way we tell ourselves the story is we say it's because the standard model fermions see the core of the monopole, which mediates baryon number violation and leads to this baryon number violating process. But actually, it turns out that this phenomenon of monopole catalysis is really independent of the microscopic structure of the monopoles. Really, what it has to do is anytime you have a global symmetry that has an anomaly, and you have a boundary in the theory, and in this case, the boundary is provided by the center of the monopole, any anomalous global symmetry ends at a boundary. And monopole catalysis is just an example of that. And so that sort of guarantees that in the standard model, anytime we put it into a unified group that gives us monopoles, this will guarantee that the standard model flavor symmetries that have anomalies will never be good symmetries if there's a monopole present, because those are precisely the symmetries broken by monopole catalysis. And the reason I'm telling you this is actually the standard model has a lot more anomalies in it than just the higher group anomalies of flavor that we already mentioned. So of course it has all of those higher group structures. That's what's in the left table here. But it also has non-invertible symmetries because standard model flavor symmetry groups have anomalies with hypercharge. And now we know that both higher group and non-invertible structures come with these emergence criteria. And so we can ask what sort of implications that might have. So I just want to draw your attention to one example. If you make the combination of the standard model U1 flavor symmetries corresponding to baryon number, that has an ABJ anomaly with hypercharge. And so you could think about it as being a non-invertible symmetry. And these emergence criteria that we discussed mean that it should be broken above the scale of monopoles that carry a hypercharge. So, okay, we know a unified theory will give us such monopoles. And so we can ask how this emergence conjecture plays out. And of course, it's trivially satisfied by SU5 and SO10 because we know those theories violate baryon number. But you could also ask about unified theories that give us monopoles, but don't have violation of baryon number baked into them. That would be true, for example, of Padi-Salam or trinification. And the answer in these cases turns out to be very interesting. In Padi-Salam, this effect was actually known, although I think not widely known in the early 80s. And of course, in Padi-Salam unification, although we put baryons and leptons or quarks and leptons into unified multiplets, baryon number is still an accidental symmetry of the gauge interactions. And so this idea that gauge bosons at the core of the monopoles are violating the symmetry is not in effect. However, the fact that there is an anomaly between hypercharge and baryon number means that there are effects that lead to baryon number violation, even though baryon number is a good classical symmetry of the unified theory. This was speculated about by Frank Wilczek, but really made precise by Sen in a series of papers in 1984. And it turns out to be a very beautiful phenomenon, breaking a baryon number through the anomaly. The baryon number violation happens by 3 units in scattering off of monopoles. So it's very unlike sort of conventional catalysis of proton decay, but nonetheless is present. And it turns out this effect also happens in trinification. So again, we think of trinification as being the best unified theory for baryon number because baryon number is a genuinely good global symmetry of the theory. But because there still is a ABJ anomaly with hypercharge and trinification gives us monopoles, there are again processes by which the monopoles of the breaking of trinification lead to violation of baryon number. And that much like in Padi-Salam, this process actually is very exotic compared to what we're used to. Baryon number violation again proceeds in multiple units through scattering off of these monopoles. And this is something that, to my knowledge, was simply passed over in the 1980s, I think because all of the ingredients weren't quite in front of people. But recognizing the global symmetry structure and the generalized symmetry structure of the standard model in modern terms makes it apparent that these effects are present. And this can have some interesting phenomenological implications. Of course, well, in the interest of time, I won't go into some details, but it turns out that the monopoles of trinification are not spherically symmetric. So there's some interesting technical questions about how these baryon number violating processes occur. And also the phenomenological consequences are potentially interesting because the scale of trinification could be lower than the scale of other forms of unification. And so there could be more experimentally accessible signs of monopole catalyzed baryon number violation. Okay, so I'm out of time, so let me bring things to an end. I've tried to give you a couple of messages in my talk this morning. One is just that generalized symmetries, of course, they're abundant in particle physics, but also how to think about the parts that are interesting to us as particle physicists, which have to do with the explicit and spontaneous breaking of these generalized symmetries. And there's been a lot of really impressive work over the last 3 years beginning to identify these symmetries and how they can act in ways that we care about as particle physicists. But I think we're in very early days in terms of figuring out exactly how much we stand to learn. I've tried to give you two examples of where I think we can learn some new things, and I know you're going to hear a lot more about some other examples throughout the talks later today, particularly I expect by Sungwoo. The two examples I gave you was one, thinking about the generalized symmetries of extra-dimensional theories allowed us to understand very clearly why extra-dimensional axions are a good solution to the quality problem. And then the second example I gave you was pointing to the higher group and non-invertible symmetries of the standard model as a reminder of the non-perturbative structures associated with unification, and in particular, monopole catalysis of global symmetry violation. And in fact, by thinking about the standard model this way, pointing out effects that were missed in the 1980s. So this is just beginning to open the box. I think there's a lot of other exciting things that we stand to learn. Again, you'll hear about many more of those later today. But thanks very much for letting me tell you about these stories this morning.
Thank you very much for the comprehensive talk. So do you have any questions? Okay.
Thanks, Nathaniel. Thanks for the great talk. Very exciting and cool to see something new is coming up. My first question is on your extra-dimensional axion. I think I totally agree that understanding what happened to the general symmetry under the compactification is a very important question. And as far as I know, there are only two papers, one in completely formal side and one yours. Therefore, my question will be, have you noticed any sort of emergent surprises under the compactification in the sense that there are any certain features happening to the axion physics which is completely invisible in purely four-dimensional field theories, for instance?
Well, I mean, so certainly the exponential goodness of the symmetry is impossible to understand, right, from the four-dimensional perspective. There is one thing which I didn't go into detail in my talk, but it follows directly from the story I gave you. So you'll notice in the story I gave you, I just compactified the fifth dimension on S1, and you might have thought I was being a little cowardly because, of course, if I just compactify an S1, I end up with an extra four-dimensional vector, right? That's not phenomenologically sensible. Mm-hmm. So, of course, what we normally do if we want sensible phenomenology is we compactify an S1 mod Z2, and then we can project out the vector zero mode, right?
Right.
And you might worry that if I've compactified on S1 mod Z2, that might do additional violence, okay, to the symmetry structure of the theory. Right. But it turns out, right, that doesn't do the important violence to the axion symmetry, right? It obviously breaks the four-dimensional electric one-form symmetry, but it preserves the fifth component, which is the shift symmetry of the axion. Right. And in fact, it allows you to understand, there's some papers by Kirosh from 23 years ago that we're interested in if you compactify an S1 mod Z2, you might worry, for example, that you could localize symmetry breaking effects, large symmetry breaking effects on the boundary, because it only has to respect the reduced symmetries of the boundary theory, right? But what they observed is there was from the 40% perspective, there was an infinite set of symmetries which prevented large corrections to the axion potential from being localized on the boundary of the extra dimension. And that infinite set of conditions can, instead of being some mysterious consequence, it can be just directly follows from the higher form symmetry. Okay, so I would say that's a good example. If you try to become more phenomenologically relevant, compactify on S1 mod Z2, something that at least 23 years ago was totally mysterious, is very naturally organized by the higher form symmetries. Now, so far, we've been very cautious about compactifications with boundaries because it is a much more complicated situation, and it is possible for bad things to happen to the generalized symmetries and that we don't totally yet understand. But in the simple example of S1 mod Z2, the higher form symmetry is still good, at least the part that we care about, and it allows us to understand this 23-year-old mystery.
Oh, that's very interesting. I don't know if that is related to sort of either anomaly influ or anomalies happening in the compactification with the fixed point. There has been interesting work. But if we put that in the context of ADS, I wonder if we can learn something more about the UV, suppression of the symmetry breaking. As you said, there cannot be localized breaking on the brain, for instance, right? They can be interpreted as why there can be UV triggered explicit breaking effect, which is sort of there's origin in the birth in a sense. So I don't know. I wonder if you thought about that, but it sounds
absolutely. In fact, it's something that I'm very actively thinking about now. Is what we learn from holography about these generalized symmetries, and of course, there's been quite a bit of work. If you have on the CFT side, if you have higher form symmetries, of course, it's well understood what that does on the ADS side. That just means there's higher form gauge fields in the bulk. Right. But of course, you could have, as we care about in RS models, if you have gauge symmetries on the ADS side, those have higher form symmetries. Now, they're not holographically exact symmetries because we expect them to be broken in the presence of gravity, but they are exponentially good. Right. And understanding what those are on the CFT side, I think, is not well understood at all. And so there's just a huge opportunity there as well. So yes, yeah, I'm just sorry I'm not there because I'm sure we would have some very useful follow-up discussions on this point.
Yeah, absolutely. Oh, okay, yeah, thanks very much. That clarified my questions. I hope to see you soon at some point, maybe in April.
Thanks.
Other question? Oh, please.
Hi, Nathaniel. Thanks for nice talk. I have a very simple question. If actions from higher dimensional gauge fields, do you still have action string that is actively studied?
I'm so glad you asked this question because indeed there's for time I took out these slides, but this is another point where thinking about the generalized symmetries is very productive because there's a sort of lore which is out there that if you have strings, field theory extra dimensional axioms, you don't have strings, right? Because or even if they come from string theory, maybe you have string theory strings, but you don't have Peche-Quinn axion strings with cores. Okay, but the beauty of thinking about this situation from the perspective of the generalized symmetries is it helps you to understand that you do have totally unexplored analogies with Peche-Quinn strings. And so just in the example I gave you, where it's a 5D U1, of course, you could have 5D monopoles in the theory, but a 5D monopole is a monopole string, right? And you could imagine, for example, it's a 't Hooft-Polyakov monopole string. So maybe your U1 in 5D came from an SU2. And then you have 5-dimensional monopole strings whose cores are the 5D SU2 and interpolating to the 5D U1. And now you can ask what happens to those string objects under dimensional reduction. And the answer is you end up with field configurations that are like vortons, where they're solutions to the 5D equations of motion, but from the 4-dimensional effective theory, they're supported by their momentum in the extra dimension. And so there's a completely analogous story involving axion string formation, where if you inflate above the scale of compactification, you can make these monopole these magnetic monopole strings. But in the 4-dimensional effective theory, they look like axion vortons. And the details of the abundance that you get from these configurations we're still working out. But the fact that you should expect to find real axion strings is clear because the 4-dimensional two-form symmetry of the axions, right? The charged objects are the string world sheets. And you could ask, what is that in 5 dimensions? And we know that's in 5 dimensions, it comes from the 2-form magnetic symmetry. And the charged objects are the world sheets of the monopole strings. So the answer is absolutely yes. There are solutions like Peche-Quinn axion strings that come from the 5D monopole strings. And the phenomenology of that we're working out right now. So it's a great question.
Okay, so in terms of 4D theory, in the core of this string, you have towers of KK modes?
That's right.
Oh, okay.
Yeah, so it's the 5D SU2 that's restored in the core. And again, you would think that these strings should just dissolve because they're not solutions to the 4D equations of motion. but they're supported by their momentum in the extra dimension. So they really are like vortons.
Okay, thank you.
Okay, maybe final question. Actually, I have a live question. So this high quality of extra-dimensional axions, do you think we have genuinely new thing that we can learn from this new mathematical formulation?
Yeah, so again, in the details that in the interest of time, I suppressed. Let me give you one example of a new effect that had not been computed until now. So we know that in 4 dimensions, if the axion couples to FF dual of an abelian group, and that abelian group has monopoles in it, we can think of loops of the monopoles as giving a contribution to the axion potential. This was nice work that was done by the Harvard and Brown groups a couple of years ago, making this concrete. They computed the Coleman-Weinberg potential for the axion that comes by integrating out monopoles of a U1 group that couples to the axion. But now you can make a very similar argument in the 5D theory, where you can say, okay, it's an example of getting the axion potential from anomalies, but not anomalies with a non-abelian group, anomalies that involve Chern-Simons terms between the U1 that the axion lives in and other U1 factors that could live in the bulk. And so if you have such a Chern-Simons term, and if you have monopole strings that are charged into those additional U1s, when those strings wrap the compactified dimension, they also give a potential to the axion in 4 dimensions. It's exponentially small, not in now the axion mass times some other scale, but it's actually exponentially small. It involves basically the tension of the monopole string in the exponent. And that's a calculation that was not performed until we understood this picture, and then working by analogy recognized that there should be contributions from monopole strings in 5 dimensions to the effective axion potential in 4 dimensions. So yes, it's not just a repackaging of things we already knew. It points us to new calculations that we hadn't done before.
Oh. Okay, let's thank Nathaniel.
Thank you very much. Thanks for the opportunity. And I'm very sorry not to be there, but I'm very glad to see you all on Zoom.
Okay, thank you, Nathaniel. Okay, so you can keep connected on Zoom if you want. We'll open the Zoom session after the break.
Great. Thanks very much.
Sungwoo will give a talk. Right? Yeah, so, yeah, Sungwoo Hong.
Yes, great. Thank you.
Okay, thank you. Okay, see you. Okay, we are kind of running out of time. Let's resume our session at 11:10. Okay, thank you.
제가 잘못 건드면 시스템을 어떻게 하는데 다운 받을 받아줘야 되죠. 올리시나요? 네, 다시 한 번만 그거를 해주시면. 네. 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 아, 아. 해볼까요? 클릭 한번 해주시면 여기. 아, 슬라이드 슬라이드 이걸 마이크 네. 그 혹시 슬라이드 여기를 안 쓰겠네. 아직 뭐 수십 초가 남은 것 같아요. 아. 모르겠어요. 네.
Okay, welcome back. Let's start second session of the morning. We have two speakers. First one is Sungwoo for 40 minutes. He'll tell us about gravitational waves. Please go ahead.
Do I use mic? Okay. Thank you. I would like to thank the organizers for inviting me and give me a chance to speak. Right. So today, I'd like to talk about ongoing recent work, which is pretty close to being done with two postdocs. One is Sungwoo Lee. He was my former postdoc who recently moved to CERN. And second is Q.U. Liang. She is a postdoc at IPMU. So as the title said, today my talk is really about the gravitational waves with certain topological defect, in this case, in particular, domain walls. And I think this will be the least generalized global symmetry related talk that I gave in the last 1.5 years or so. But nevertheless, you will see at least one slide with the generalized symmetry. Okay. Good. So here's my brief introduction. The way I think about this project and a lot of ongoing projects related to the topological defect is this. I think the study of phases of the universe, just like phases of condensed matter systems, such as conductor, superconductor, topological insulator, and so on and so forth, that is, I think, very interesting and important to understand. In fact, we've been doing that all the way through. For instance, So this is a quick snapshot of the evolution of our universe. And then we've been organizing different phases of the universe according to which sort of energy density dominates at given time. For instance, so our universe has gone through a long period of radiation dominance, and then it has started doing certain new phases in terms of matter domination. And then very recently, we believe that our universe went into the different phases in terms of dark energy. And in order to address other important problems, such as monopole and horizon problems, we hypothesize probably we need another phase in our universe in terms of dark energy. And obviously, depending on which phase we're talking about, there are characteristic events which are crucial for us to understand in depth what happened in the past in our universe. For instance, radiation dominance allowed us to think about the thermalization process, and therefore there's a lot of intrinsic generations of necessary ingredient of our universe, such as light element and BAU and the dark matter and so on and so forth. A matter dominance is allowed to construct and create a larger scales and so on. All right, and each time we go from one phase to the other, obviously another very interesting event in the cosmological history happened. For instance, as we go from, as you know, dark energy to the radiation, reheating happened, and as we cross from a radiation to the matter dominance, for instance, the CMB was produced, right? So why am I talking about this? Well, once again, I really think that the understanding deeply enough all possible choices of phases of our universe is absolutely crucial. And here, one small but very obvious point to make is that in addition to particles that we've been dealing with so far, obviously a lot of field theoretic and then gravitational description of a universe, a lot to talk about topological defect. So one way to think about this existence of topological defect is that if we have a field theory construction where in the UV, meaning high temperature, we have a theory in terms of certain gauge group G, or not gauge group, sorry, global symmetry group G, or it can be gauge sometimes. And then for some reason, if this is spontaneously broken down to a subgroup H, then we are in a moment of thinking about various kind of topological defects. So for instance, if the zeroth homotopy group of the G mod H, meaning this is a coset, is non-trivial, then cosmology can produce a domain walls. And if the first homotopy group, pi 1, is non-trivial, then cosmic string can form, and pi 2 is non-trivial, topological monopole can form, for instance. And all kind of hybrid object can, in principle, exist, depending on if there are a cascade process of symmetry breaking. So, in addition to the particle, it is extremely natural and ubiquitous that topological defect indeed can be produced. And these are not, by the way, a coincidence, right? So why 0, 1, 2, and so on. But first, that's because domain wall is a three-dimensional object in four-dimensional space and time, and it is probed or measured by a local operator, okay? So that's why there's a 0 there, zero-dimensional object. And cosmic string being a two-dimensional object in four-dimensional space and time, which are charged under, for instance, two-form global symmetry and can be measured if we have a one-dimensional symmetry defect operator. Hence, there's a 1 here. Likewise, there's a monopole, which is like zero-dimensional object at the fixed time, but that corresponds to one-form symmetry object, and then it is probed and linked by two-dimensional symmetry defect operator. That's why there's a 2. Okay, so all this can be recasted and we understand in terms of all generalized global symmetry language as well. Since I just mentioned generalized global symmetry, I think it is very non-trivial in the following sense. So in recent years, and then a lot more to happen in the future, I think now physics, in particular particle physics, in terms of or together with generalized symmetry, is now a new and promising direction to pursue. I strongly believe that. And in general, such theories, any quantum field theory, in particle physics, with the generalized global symmetry predicts the existence of topological defect, very often not conventional type, but new type and new ways of interaction among the topological defect. And therefore, they sometimes provide best probe, or sometimes even the only probe of certain physics. So for instance, in the case where your QFT has a TQFT coupling, meaning you have a standard model or some other particle interaction sector coupled to a sector of topological quantum field theory, you start having new types of a topological defect or new properties of topological defect. And another very important question that getting attention these days is what's known as the global structure of a standard model gauge group. And in such a case, it also seems like a topological defect plays a crucial role. So anyway, here, this is a small slide about the fact that whenever we have a quantum field theory, in terms of generalized global symmetry, very ubiquitously, it predicts a existing topological defect, and they may play also important role in cosmology as well. Now, let me be more concrete now. So here is a snapshot of my universe again, and I'm just showing you this dark energy dominance, radiation, matter, and dark energy dominance again. And like I said, existence of topological defect is ubiquitous, and you can speculate whether it is reasonable to think about there's any phase in any time in the universe where this period of time is dominated by a existence topological defect. Okay, so it is reasonable to ask whether topological defect dominance can occur, and if so, how would cosmology look like, and how we test those scenarios. Okay, so this is not just a single speculation, actually. So it is not actually new. People already thought about and studied topological defect dominance. For instance, so let's recall that monopole energy density, which behaves like a particle, literally behaves like a matter. And in that case, if we had a heavy monopole, they naturally dominate the universe. In that case, we are in the moment of worrying about the monopole problem. And in the case of a cosmic string, it turns out that once they enter what is known as a scaling regime, which I will discuss a little bit later, turns out that their energy density behaves like a radiation. So we don't actually have, say, cosmic string problem, but nevertheless, they can provide many interesting signatures. Lastly, domain wall, if they enter again what's known as a scaling regime, which I will discuss, turns out that their energy density goes like tension of the wall divided by the cosmic time, the actual physical time. You may want to compare this with how radiation energy density drops. In this case, it drops like a 1/t squared. So the energy density of the wall decreases slowly compared to the radiation and also compared to the matter. Therefore, if we have a stable domain wall, they naturally dominate energy budget of the universe. So we call, as a community, this problem as a domain wall problem. So far, the way the community perceive this issue or this feature is that, well, that's bad, because if we had a domain wall, if they're stable, looks like very naturally they will dominate our universe. And our current, very recent observation is completely in contradiction with that. Therefore, we want to avoid that. So far, the perception has been that whenever we have a domain wall, we want to kill it. So that's how we have seen and played with these domain walls. But is that true? Are we that if we have any phase in the universe where domain will actually dominate the universe? Okay. The answer is yes, if they dominated pretty recently, but no, not at all if actually dominate early in the history of cosmology. So in this talk and in this work, we consider the domain wall dominance and ask just what happened to it and how would the universe look like, and if so, can we actually test the scenario at all? All right. So the first bullet point is that yes, domain wall dominance is very, very natural. They really yell out to become a dominant energy source. And all theoretical construction we consider so far is just try to kill that part and then never allow domain wall dominance. So why not? Therefore, usually people try to stop the domain wall dominance by making domain wall unstable, and there has been several theoretical constructions, and more is under play. However, hopefully, as I convey today, there are really fascinating features of domain wall dominance. And in fact, it can be well probed by gravitational wave signatures. All right, so with that, let me move on to the next part of the talk. Here, I want to talk about domain walls in more conventional, more familiar time, which is, in this case, I consider radiation dominance. But most of what I will say here in this part applies to matter dominance as well. So let's first talk about the formation of the domain wall, which is according to a Kibble-Zurek mechanism. So how does that work? So just to be concrete, let's consider Z2 case. Okay, phase transition happens. You have two vacua. One is plus, the other is minus. And then within a patch controlled by the correlation length C, there's a coherent phases, either plus or minus, plus minus. There's a random distribution. This is controlled by completely statistics. Okay, not yet. Dynamics has not kicked in yet. Okay, and then this size of the correlation function, it can be different whether phase transition is the first order or second order. But regardless, the correlation length can never be larger than this Hubble patch, okay, by the causality. So once that distribution happens, then you can try to see where, the boundary between the different two phases, in this case, plus and minus, that's where domain wall arises, okay. Now, it is well known, according to the percolation theory, that if the probability for plus a vacuum happens or minus vacuum happens is greater than a certain critical probability, turns out that percolation happened, which means that now you have infinite size, either plus patch or minus patch. And typically, this critical probability is less than 0.5 for a three-dimensional situation that we're talking about. And to be concrete, for instance, if we consider cubic lattice, in order to actually, consider concrete mathematical setup, turns out the PC can be, for instance, roughly 0.3. So, for instance, this Z2 case, percolation definitely happened in a lot of cases with domain wall is predicted in the quantum field theory. Percolation can naturally happen. Now, in that case, you get, gigantic infinite size cluster. But turns out that we can also understand what happened to the finite size cluster. For instance, in this case, this example doesn't show, but for instance, if you had a minus here, you can consider there's a one finite cluster here. And turns out they're typically suppressed. There's a typically suppressed exponentially according to the size of that cluster, for instance. So this is what happened at the formation of the domain wall. And you can now combine this picture to conclude the following picture. So domain wall network typically dominated by a single infinite wall with very complicated topology. There might be a few finite closed walls with a typical size R, which is controlled by the correlation length. Okay, that's the size where you can have a coherent phases. Closed walls with a size much larger than correlation lengths are exponentially rare. So basically, therefore, if you combine all this information, once a formation happens, domain wall network within a single co-moving Hubble patch, which I'm using AH to the inverse, that's the size of the Hubble patch in co-moving coordinate system, will be like something like this. There's a single gigantic domain wall with complicated topology, and there might be a few small, closed walls, but I'm forgetting about them because they're not dominating the energy budget of the universe. So that's the initial condition. Now, what about the dynamics? Now I want to talk about briefly the evolution of the domain wall network. So once that happens, so consider this one gigantic infinite cluster with, for instance, if I zoom into this part, they will have a characteristic curvature scale of the order of R. So that's what I'm saying here. This is like a rubber sheet. So if you have this curvature with the curvature radius R, the tension of that, which goes like, sigma over R, will tend to stretch out these structures. Okay, so any irregularities will want to stretch out by the causal dynamics. So as they do, this part of the wall speed up, gets accelerated, and then there's a velocity picked up. But there's a second important force. So as this wall trying to travel through this, there's a cosmic plasma filling this part of the space and time, and then there's interaction between the two. Therefore, there's a friction. So there's a friction which goes like roughly number density of the particle interacting with a wall, and then momentum transfer for each collision can provide. And one can estimate that to be roughly tempered to the force times the velocity v. Okay, so there are two forces. There's one is the tension, the other is the friction that's acting on the wall. And then this velocity now can be estimated to be determined by balancing these two forces, okay, tension and the friction. And there's some expressions you can see, but anyway, so the velocity, one important point here is that typically grow with time, meaning it gets accelerated. One can do a slightly better job. Okay, so suppose there's a curvature R, which gets stretched out in time t sub d. That's I call a dissipation time. Okay, assuming this stretching process happens within a Hubble time, here I'm denoting, then one can do slightly more sophisticated and then refined analysis. Then turns out that the velocity of the wall, meaning a rubber sheet gets stretched out, can be estimated with this. There's a Planck scale, tension, and the time. In particular, as you see here, velocity gets increased, like t to the half. You can do the same thing. What happened to the curvature radius? You see the curvature radius gets also increased. In this case, it goes like t to the 3/2. So at this point, the picture is that you have a very complicated wall, and then because of the tension, it gets stretched out, and then velocity goes up, the curvature radius increases. And at some point, you would expect that now wall moves at relativistic speed, and you can estimate when that happens. And it turns out that that time when this wall moves like a relativistic speed goes like a 1/g sigma, where sigma is once again the tension of the wall. And at that point, the characteristic curvature scale is now of the order of the Hubble. Okay, so they stretch it all the way to the scale of the Hubble patch itself. So that's roughly speaking how domain wall network evolves. At that point, we learn something very important. Okay, at that point, what happens is the following. One can check that now domain wall energy density. Once that happens, first you can check that the energy density of the wall is now comparable to the critical energy density, which means that once that happens, domain wall energy density start dominating the universe. Second, exactly around the same time, domain wall energy density now goes like a sigma over just time, sigma over t. Okay, and this is correlated obviously. Okay, because now domain wall energy decreases much slowly compared to the radiation that can start to dominate the universe. And in particular, this behavior where the domain wall energy density goes like a 1/t is known as a scaling solution. So what is a scaling solution? You have a complicated wall, okay? And then co-moving Hubble patch during the radiation increases. More work comes in. They do the dynamics that stretch out. And then co-moving Hubble patch increases again. More walls comes in, but they will be curved, and then they will stretch it out again. So this stretching process happens so quickly that as the universe increases, therefore co-moving Hubble patch increases, wall configuration more or less looks the same. Okay, scaling. Okay, so it's self-similar configurations. So far nothing is new. I just sort of review what has been discussed in the literature. The last thing I want to say, which will be really important, is that the evolution of the domain wall on super horizon. So you have a co-moving Hubble patch. There will be a domain wall outside of horizon too. What happened to them is that both amplitude and the wavelength, meaning the size of the wiggle and the frequency they move around, basically conformally stretch out. What that means is that there's a wall outside of the Hubble. They basically move according to the expansion of the universe. Nothing happens. There's no actual dynamics with respect to the frame. Okay? So they literally is like a dead body. They're just floating and then expand according to the expansion of the universe. So on the super horizon, they basically conformally stretch out. And shape doesn't change. Okay, so far that is what happened to the domain wall in radiation dominance. So now let's actually march into a domain wall dominance region. Okay, so now I'm going to walk from a radiation dominance to domain wall dominance and then exit to the radiation dominance again. Okay, so as I discussed, as we go from the radiation dominance, for instance, obviously one can consider matter dominance also, but there's nothing changed, but not much change. There's no much change, even if we consider matter dominance. But anyway, for this talk, I'm just going to consider radiation dominance. And then as we go towards the domain wall dominance, which means that there's a domain wall energy density according to the scaling regime. There's a critical energy density according to radiation. They're sort of now of the order, same order. And then one can estimate once again that wall equality, as opposed to the just matter radiation equality, I just use the wall equality, happens roughly at the time 1/g times sigma. Now, in terms of a wall geometry, there is a curvature scale that goes towards the size of the Hubble as we getting approach to the wall equality, after that, you cannot have a larger scale. So in that sense, now coordinate scale just expand according to the expansion of the universe. Okay, so now wall curvature radius scales like scale vector itself. So because of this, then domain wall energy density of the domain wall network, which always goes like a sigma over R, okay, now goes like sigma over A instead of sigma over T. So you start deviating from a scaling solution. In this case, it basically behaves like a single infinite wall stretching out. Now, what about evolution? So here is a quick calculation one can do. So once we know that domain wall energy density behaves like a sigma over scale factor A, then from a Friedman equation, one can check that in that regime, once the dominant energy density of the universe is domain wall, then scale factor goes like a T square. Okay, so this can be compared to T to the half for radiation and T to the two-thirds matter. You might say, okay, it's different numbers. So what's so different about it? Well, there's a crucial difference between whether this power is greater than 1 or smaller than 1, as you will see momentarily. Okay, there's a critical difference between these two. You can also sort of derive effective equation of a state by using a continuity equation. In this case, you will get the omega for domain wall dominance period is minus 2/3 as opposed to being 1/3 for the radiation or 0 for the matter. Again, you get this minus sign here. But anyway, so these two factors, which you can check quickly once you understand you're in the domain wall dominance, will make a real difference. So here's the first moment that you will see the characteristic feature of a domain wall dominance. So first, let's consider co-moving Hubble radius. So this is a typical, if you like, a size of the Hubble patch within which you can expect to have a causal dynamics. Outside of that, basically things are frozen. Okay, so this is basically boundary is setting up a causal dynamics. So anyway, you can compute it, and the radiation co-moving Hubble radius increases like A. Matter, it increases like A to the half, so slightly slowly compared to the radiation. Now in domain wall dominance, you see that this co-moving Hubble radius actually decreases as the universe increases. Another way of phrasing the similar phenomena is if you compute, so given A to the T, A is a T to the some number, okay, I show here, so either T square versus T half, T to the 2/3. Given that, you can compute the acceleration of expansion of the universe, and obviously from this you can get this formula. What is crucial is this prefactor, okay? So this prefactor will be positive if lambda is greater than 1. What that means is that in domain wall dominance, universe actually accelerate and it expand. And either for radiation or matter dominance, since lambda is less than 1, this actually is negative. That means that universe decelerate. So this may, make you think of inflations. In that sense, domain wall dominance is a sort of inflating phase, but not as critical or dramatic as actual inflation do, but nevertheless give you sort of accelerating phase with a decreasing of Hubble radius, co-moving Hubble radius. So I can put all this together to make the following sort of evolution picture. Okay, so here's my inflation. Here, scale factor increases exponentially and co-moving Hubble radius decreases exponentially. So it's very rapid decrease in terms of co-moving radius. And then there's a radiation after the reheating. There's an increase of co-moving radius. There's another radiation, and then finally matter, and then finally there's a dark energy. But here, the most important thing is this domain wall dominance where co-moving radius actually decreases. Okay. So you might say, cool, there's some new features. So what about it? This will imply two significant features for the discussion that I want to continue next. First, this decrease means that the size of a co-moving Hubble radius can be much larger than what you can do just based on naive extrapolation of radiation dominance. So if you continue to use radiation dominance, you would expect that by this time, during this time, The actual size of co-moving radius should be that. On the other hand, if you had a domain dominance, then this can be much, much larger. This implies that the number and the size of the co-moving Hubble patch that we can expect to probe from the perspective of today can be vastly different than what we can expect just based on organic radiation dominance. So let me just show you this again. So this I took from Daniel Bauma's cosmology lecture note. So this is today, okay? This actually shows evolution of co-moving Hubble patch. And then if this is what's known as a particle horizon, and this is the amount of part of the universe that we can actually see any signal from. So for instance, if we also go back, the size of Hubble patch, co-moving Hubble patch during the time of CMB is this, which means that since everything inside of that I can see, I can imagine there's a lot of patches of this size that I can actually collect entire data from. Now, then going back to this picture, on the other hand, if there were any domain dominance, the actual size of the Hubble patch can be vastly different from your naive expectation. Okay, so therefore the number of patches can be different, but also crucially, the characteristic wavelengths of any physics happening can also be vastly different. Because as we will discuss, characteristic wavelengths is basically controlled by the co-moving Hubble patch. So if the co-moving Hubble patch, the size is different, obviously characteristic frequency of any physics can also be different. Okay, so that's the first significant features of having a domain dominance. The second feature is also very strikingly important. The decrease in this co-moving Hubble radius during the domain dominant phase means that this provides us very good preservation of any signal, including gravitational wave, that is produced either during or before that epoch. Oh, did I have typo improvement? Can larger than naive experience? No, it is a larger, right? So this is actually the size of co-moving Hubble patch. If I had a domain dominance, if I didn't, I will have this size. It can be larger. Yeah, so this is like standard radiation. And suppose I didn't have this, then universe will continue to do this, right? Then, for instance, co-moving Hubble radius at that time is this size, but since if I have a domain dominance, all of a sudden the co-moving Hubble radius is much larger. That's what I meant. Unless I didn't correct. Yes. Oh, you're thinking that way. Oh, if you think that way, you're right. But we are doing archaeology. So what we know is here, and then we just extrapolate backward all the way. So that's why I'm saying that it's much larger. But yes, we are both right. It's just we took a different basis. Very good. Okay. The right side. Oh, sorry. Well, did I make? Oh, this should be MD. You're right. That's what you meant. Was that what you were saying? Oh, this is typo. Sorry, this should be MD. Sorry about that. Yeah. That's a actual typo. All right, good. Okay, so the second feature of a domain dominance is that this will provide us a period of extremely good preservation of a gravitational wave produced either during domain dominance or before. Okay, so let me make this picture more clear. Suppose universe just had gone through just a radiation dominance overlap. And then suppose I had a gravitational wave produced sometime like that. Okay, so then gravitational wave will propagate in the universe, which is almost always like sub-horizon, because this is my horizon. And as we'll discuss, if there is a sub-horizon propagation, then first of all, the H metric dilutes like 1/8, and therefore gravitational energy will dilute like 1/8 to the 4th. However, now if you look at actual this evolution together with the domain dominance, then this gravitational wave exits the horizon pretty quickly, and for a long time, it lives on the superhorizon, and it only enters the horizon very late time. What that means is that on the superhorizon, once again, as I will discuss briefly, the gravitational wave does not actually decrease. H does not decrease. So this provides us a long period of good preservation of gravitational wave. Okay, so as you will see, therefore, we have a surprisingly strong and sensitive probe of a super early universe if there were any domain diamonds. Okay, so with that, let me move on to the last part of my talk. Let's make sure I'm on track. Okay, good. So now I want to talk about actual gravitational wave probe of these domain diamonds. Okay, so let's first talk about gravitational wave production, in case you haven't thought about it. So let's first review ourselves. How should we think about the GW production during the radiation dominance once the domain network entered a scaling region, okay? So as I discussed briefly, once we are in the scaling regime, the characteristic curvature scale is of the order of Hubble. So this is my co-moving Hubble patch, green, and this is my domain wall. So during the scaling regime in the radiation dominance, the characteristic curvature scale of the domain wall is of the order of a Hubble radius. And then they will do song and dance, like that, okay? So then gravitational wave power, meaning energy per time, can be estimated using what is known as Einstein's quadruple formula, okay? So G times the source, basically. The source is a square, expectation value of a square of triple time derivative of a quadruple moment. Okay, so that looks a lot of dots, but that's true. Okay, that's not a mistake. So this Q is quadruple moment, which means that there's, roughly speaking, for domain wall, there is a mass times T squared, in this case R squared, but R is roughly of the order of a Hubble because there's a single scale. Everything is T. So this is MT squared, and then M, the domain wall mass, is a tension times area. So area goes like T squared. Everything is T. Single scale, self-similar evolution. And you can put back everything to this, and then you get Q triple dot goes like sigma times T. Because every single dot is 1 over T, so you can just estimate like that. And then you can plug in, and then therefore a gravitational wave power produced at a given time goes like G sigma square. That makes sense. You need a two body, and then they do the song and dance, and then T squared. You can also compute if you wish, power density, which means the power divided by the volume, or the number of a mode that actually producing a gravitational wave. So we just divide it by the T cube because that's the volume within this ball, and we get G sigma square over T. So that's usually how we can estimate roughly gravitational wave production during the scaling region. Okay, so far review. Now let's talk about something new. And you can ask what happened if we are in now domain dominance, first of all. Okay, so let's recall that during the period, the co-moving Hubble patch decreases. So let's imagine a time soon after the domain dominance. There's a Hubble patch, and this is the domain wall. Okay, passing through that patch. Again, hopefully it's clear that this is of the order of this Hubble radius. Okay, 5 minutes. Okay, probably that might be enough for me. Okay. However, again, during the domain dominance, Hubble patch decreases. So from this big one, reduce down to the small one. Okay. Now, once that happens, the actual fluctuation is not controlled by this size, not the entire, Hubble radius. So one can estimate doing quick geometry. This fluctuation size now goes like R as in the previous slide, but there's a suppression factor. Okay, roughly speaking, this is theta square of whatever cosine. Okay, one can estimate that. Therefore, now one can plug in everything, assuming the characteristic frequencies is still the Hubble of that patch, and then one can find out that gravitational wave production during the domain dominance is much suppressed compared to the scaling regime before. Okay, so here lesson number one. Yes, so if there's a phase transition happens, there's a gravitational wave production happens during the scaling regime. And then what I'm showing here is that gravitational wave production during the domain wall dominance, on the other hand, is much, much suppressed. So is that boring then? No, I told you. Now, therefore, what we have to think about is that since production of phase transition that produces domain wall, there will be scaling regime that produces a gravitational wave. Even though we can sort of forget about the gravitational wave production during the domain wall dominance, nevertheless, now we have to take into account the evolution of that. And in that part, we have a huge difference. Okay, because I told you there's a strong preservation of gravitational wave because of this domain wall dominance. We can understand the evolution by solving linearized Einstein equation. This is just the formula to show that there's such a thing, equation exists. We can solve it analytically. On sub-horizon, once you are in the horizon, if the frequency of the gravitational wave is, in this case, higher than co-moving frequency, if you like, then one can show that the H, the metric, decreases like 1/a. Okay, so on sub-horizon, as it propagates, the H drops. On super-horizon, on the other hand, well, again, you can solve this problem showing that the metric doesn't evolve, okay? It preserved on super-horizon. And we can, therefore, organize our calculation according to what is known as the transfer function. So starting from emitting time, so imagine there's a time where a gravitational wave is emitted by the Sungwoo density of the wall. And then I want to know what is the size of metric today by having a transfer function that connects between these 2 points. So this is a quick sort of a picture to show how we might compute the transfer function. So again, this is the same picture. Let's imagine there's a phase transition. Let me imagine that there's this single point where there's a gravitational wave produced. There are a couple of regimes we can think about. So first of all, let me denote the size of this part to be KD, where D denotes the decay of the domain wall and end of the domain wall dominance. And then this, let me denote the size of this one to be K wall equality to the inverse, okay? Then I can imagine that the gravitational wave whose size is below this, meaning it is in the small scale, which means the high frequency, or between these two, or between these two, or beyond that, okay? So we can consider different wave number of gravitational wave even for a fixed time. And each time you can figure out the transfer function. So let's first quickly look at this. So if the gravitational wave has a frequency which is smaller, in this case actually larger than this, then you see that the gravitational wave propagates all the time sub-horizon. And on sub-horizon, there should be a suppression by 1/a. That's what basically this transfer function tells you. What about the gravitational wave versus happening between these two frequencies? Then you see for a while it has to go through the sub-horizon. Therefore, there should be suppression factor between AE to the A2. So that's why you see here. And then it goes on to the super horizon, no suppression. And then it enters again at A3. And then you should get another suppression factor. So in this way, yes, you can figure out a transfer function of every kind. For instance, last one, if you look at the super low frequency mode, then they have been completely preserved all the way until A3 point, and only then you start getting the suppression factors. Okay, so this therefore characterizes the features of gravitational wave spectrum if you had a domain wall dominance. Okay, so there's some detail how you might want to analyze the details of a gravitational wave, but let me skip it. Therefore, let me just share with you a few of the main results. The first one, I have one more slide to be done. So this is showing, for instance, the parameter space in terms of a tension scale, and then the temperature when domain wall decay happen and the domain wall dominance end. So we are showing two benchmark points. The first one, the tension is an order of 10 to the 10 GeV, and the decay temperature is 10 to the 5 GeV. That shows here. And then, oh, sorry, this is typo again. This benchmark 2. The second benchmark, we take a tension scale to be 10 to the 15 GeV, and then decay temperature is 10 to the 11 GeV. But you see that you can explore everywhere here. And this region shows that there's no domain wall dominance happens. And then this green part shows that in that case, domain wall network create too large inhomogeneity to be seen at either at CMB large scale structure. So it is ruled out. And this blue band shows that if you had a domain wall network, according to these parameters, then you must have produced already too large inhomogeneity to be seen by the CMB BMOS. They're ruled out. And this is hypothetical part of the parameter space can potentially either explain or constrained by recent PTA observations. So anyway, one of the points to show this is that we can certainly tackle the deep domain wall dominance, well probed, and then the scale of the probing we're talking about is a super high energy scale. And the last one, probably you were expecting to see exactly this picture, is the following. So this is, in a sense, last slide. This is showing the gravitational energy density as a function of today's frequency of observation. So the two benchmark points we picked basically can be probed around this region where frequency is either 10 to minus 2 to 10-ish hertz. This is a region where it can be probed either by LISA or in this case, LIGO band or LIGO region or Einstein telescope, and something that covers in between, for instance, the DESICO. Okay, and then you see that there's certain features we are sort of showing in that, which corresponds to what's known as causality tail. But in some cases, we can see a really genuine domain wall dominance-driven spectrum features, such as this kink, as you see here. But let me not go into the detail. So in case you have a question, I love to address. Thanks for your attention.
Oh. Any questions? You have to come over here, or you have to shout. No.
Very good. Yes, your intuition is definitely correct, and I think it will be helpful if I show this. So just like a PTA, CMB observation has like deep tip around this point. Okay, and then if you have a domain wall tail, because the CMB BMOD constraint is so deep, even though it's a single point, even the tail can be sometimes probed. That's why it provides sensitivity. Even the peak frequency is way far away from the CMB region, because CMB tip is so deep that the causality tail can be probed. That's why. So that will depend on what is the source of. So it helps, first of all, because starting from today we have a CMB epoch, and then there's a causality problem, right? Horizon problem. Domain wall period can relax that a little bit, power law-like, not exponentially. Okay, so indeed, we haven't checked the number, but it should be pretty quick. That at least it will relax the number of EFOL you need for inflation, for sure. Yes, thanks. Yes. Very good. Right. So I sort of listed 4 sort of well-known mechanisms to destroy the domain wall. The first one is the most typical one is to add explicit breaking term, which will lead to the bias term potential for domain wall. Therefore, there is a tilt of the energy, and then there's a decay. The second one is if your theory also admit a cosmic string, then domain wall can be destroyed by nucleation of the cosmic string, and then they expand and they can destroy. Third is that if the symmetry, discrete symmetry responsible for production of domain wall is temporarily restored, okay, by the Rangacker mechanism, then because of this sudden dynamics, then it can also destroy meltdown. The final thing is what's known as the Lazaride-Shafi mechanism. So in this case, the discrete symmetry that you use to generate the domain wall, you gauge it. So just like if you had a shift symmetry, you have the Goldson boson. If it's lower symmetry, if you gauge it, you disappear and it goes into the longitudinal mode gauge boson. However, there's a theoretical subtlety there is ongoing discussion happening these days. So some of these things we expect can destroy the domain wall to end the domain wall dominance, but certainly more investigation will be desired.
Okay, maybe one last question.
Can you say dynamical calculation, you mean so the calculation of the domain network evolution dynamically? Is that what you mean? Oh, good. So good. So I'll just answer very quickly for the sake of time. So one thing that we have understood, and probably is also discussed briefly in the Valenkin's book, is that usual method in terms of bias term actually will not destroy the domain wall. They will actually protect the domain wall. Okay, I can explain why. So all of a sudden, killer turns into the guardian. Okay. However, cosmic string nucleation we believe should work, and probably it's one of the best options we have. In that case, we need a sort of degeneracy of scale in the sense that scale where cosmic string is produced cannot be too far away from the scale when the domain wall is produced. But I can definitely imagine that it can be created. So such a theory can be created.
Okay, so I'm sure you have a lot of questions, but let's move on. Let's thank Sungwoo again.
Thanks very much.
Next speaker is Junichiro Kawamura. He tells us about Goldstone bosons from Goldstone bosons from